coming to the next topic, which is permutation or the alternative symbol. So, this is also called the Levi-Civita symbol, okay. And in 3 dimensions it is defined as following expression, which is given over here. It is represented by the symbol epsilon, and it has 3 subscript I, j and k, okay. In some of the literature you can find that instead of epsilon they also use e, okay. So, it is not a standard symbol epsilon, but for this course we will stick to this symbol. So, this permutation or the alternative symbol has 3 values, okay. It is +1 if I, j, k is in this order 1, 2, 3 or 2, 3, 1 or 3, 1, 2, okay. It has a value of -1 if I, j, k are in this particular order 3, 2, 1, okay, 1, 3, 2 or 2, 1, 3. For all other values of I, j, k, if I is equal to j or j is equal to k or if k is equal to I, if any of the index is same as the other index, okay, then the value of this permutation symbol is 0, okay. If I, j, k form an even permutation of 1, 2, 3, which is shown here in this particular picture, okay. So, you can see we have written 1, okay, 2, 3 in a particular order, and if I, j, k, okay, is 1, 2 or 3, they follow this order, or they are 2, 3, 1 or 3, 1, 2, okay. In that case epsilon I, j, k will take the value of +1, okay. So, this is called the even permutation. In the odd permutation, okay, this order gets reversed, okay. So, you can see here initially it was anti-clockwise direction, now the direction has become clockwise. So, if I, j, k take the values 1, 3, 1, 3, 2 or 3, 2, 1 or 2, 1, 3. In that case, the value of the permutation symbol will be equal to -1, okay. Another important property, okay, that you can yourself figure it out is that if you have epsilon I, j, k and if you reverse any 2 indices, okay, say for example here, if I interchange I with j, okay, in that case, okay, so you have I, okay, so you have j, you have k, okay, so you have this particular order, okay. So, the value is +1, okay. Now, if you interchange, so if you interchange I and j, okay, so what will happen? You will have j, I and k, okay. So, what has happened to the order? It has reversed. So, now you have -1, okay. So, this was epsilon I, j, k and this is epsilon j, I, k, okay. So, the value of epsilon I, j, k is -1, epsilon I, j, k is +1. So, this will be equal to -1 times epsilon j, I, k, and that is what you have it here, okay. And if you reverse one more time, if you interchange I and k here, okay. So, then one more minus sign will come and these 2 minus signs will become plus. So, epsilon I, j, k is same as epsilon j, k, I, okay. So, this property is very useful when you are deriving expressions, okay, and when you are going through your equations in indicial notation. So, this comes very handy, okay. So, one of the application of permutation symbol is when one needs to express the cross product of 2 vectors in indicial notation, okay. So, take for example, you are given 2 vectors A and B, okay. So, A and B are 2 vectors And now we wish to write the cross product of these two vectors in indicial notation. Okay. So, the cross product of two vectors is A cross B, and you know the cross product of two vectors also gives you another vector. Okay. So, the way the cross product is written is epsilon I j k b j a j b k e I. Okay. So, the coefficient of this base vector E I, okay, basis vector E I is epsilon I j k a j b k. Okay. So, that is how the permutation symbol enables you to write the cross product of two vectors in indicial notation. Okay. So, now to verify that this is indeed the case, what I suggest you do is you expand the right hand side. Okay. So, the right hand side you can see both I mean all three indices I, j and k are repeated index. Okay. So, which means a summation is implied over these indices. So, what you can do is you can expand this in using the concepts that we discussed in the last slides, and then you can indeed show that this single expression on the right hand side is indeed what is given by A cross B. Okay. So, that is a task for you. You expand the right hand side and show that the right hand side is indeed a valid expression. Okay. So, if you do this, you will come to know that, and you will appreciate that how indicial notation helps you to write concisely very long expressions. Okay. So, another very important relation is the relation between the permutation symbol and the Kronecker delta. Okay. So, this relation is shown here, and this is also called as the epsilon delta or the E delta identity. Okay. So, what this identity says? This identity says that if you have a product of two alternative symbols, okay, in which at least one of the indices is common. Okay. So, if you look here, the first permutation symbol has I, and also the second permutation symbol has I at the same place, okay, and the other two indices in the first alternative symbol are j and k, while in the second alternative symbol it is L and M. Okay. So, using this you can convert, using this identity you can convert the expression containing two alternative symbols with at least one repeated index in terms of the Kronecker delta. Okay. So, that is how you do it. Epsilon I j k, epsilon I L M is delta j L, delta k M, delta j M, delta k L. Okay. So, the proof of this identity we are not discussing in this course, okay, but you can very well find, and if you have any question on how to do it, you can always approach me. Okay. So, the way to remember this identity, and this identity comes very handy. Okay. So, the way to remember this identity is, see, J is what? Okay. So, we write J, K, and we write L, M. Okay. So, this we call outer, this is inner, this is inner, this is outer. Okay. So, on the right hand side, if you see delta J L, which is outer inner, okay, and delta K M, which is inner outer, minus delta J M, which is outer outer, and delta K L, which is inner inner. Okay. So, this is like outer inner, inner outer, minus outer inner. So, that is one way you can remember this identity. Of course, when you repeat, I mean when you do a lot of examples, this becomes very easy to remember, okay. But initially you have to remember it this way it helps, okay. So, now let us look into one of the application of the permutation symbol and how it helps us to prove certain vector identities, okay. So, suppose you have been asked to simplify this expression A cross B cross C, okay. Now, you can do this very well using the concepts that you have discussed, I mean that you know from your school days, but here we will like to address this simplification through indicial notation, okay. Why we will like to do this is because we want to practice our indicial notation, okay. So, let us start. First we notice that B cross C is also a vector D, okay. So, let us say let B cross C be a vector D, okay. So, then we can have A cross D, okay. Now, this can be written as in indicial notation as epsilon I j k A j D k, okay. And for this particular proof, we will not write the base vector E I, okay. So, because whatever is true for one component of a vector or this quantity will be true for all other component. So, we will just take one ith component. So, this is what is the ith component, okay. So, this is the ith component, okay. Now, let us say the first is equation 1, this is equation 2, okay. Now, what will be dk, okay. So, from equation 1 dk will be epsilon k, because this corresponds to the kth component epsilon k, and because in expression 2 I is a free index, I cannot use I here, okay, and j in expression 2 j is already occurring twice. So, I cannot use j also. So, what I will do? I will use L and M, okay. So, this becomes epsilon k L M and B L C M. So, using expression 1, okay. So, now I can put 3 in expression 2, okay. So, what I get? I get epsilon I j k epsilon k L M A j B L C M, okay. Now, there are two permutation symbols and I see there is a common index k, okay. So, this I can write epsilon I j k epsilon, and now you have k L M, okay. You have k L M, I can write this as L M k, okay, L M k A j B L C M. And now I can apply, let us say I will just rub this, let us change the index of the first permutation symbol, okay. I j k will be same as k I j, okay, k I j, okay. So, I will write epsilon k I j epsilon k L M A j B L C M, okay. Now, I can apply the E delta identity or the epsilon delta identity that we just discussed, okay. So, why I have done this is because I want to match the repeated index in my expression with one which I mentioned above in the E delta identity. Okay. So, the two permutation symbols can be written in terms of the Kronecker delta as epsilon I k outer inner. Okay. No, sorry. Okay. So, let me rub this, yeah, epsilon I L, okay, outer inner, inner outer, which is inner is j, outer is m. So, delta j m minus delta inner inner I L outer outer j m, okay, A j B L C m. Okay. So, now let me make some space here, I will rub this and I will continue from the top. Okay. So, now I have the Kronecker deltas and I can open up the brackets and use the substitution property of the Kronecker delta. So, this I will leave it to you. I will write directly the final expression. You expand the brackets, okay, open up the bracket and use the substitution property. So, what you will have is B I, okay, A m C m minus, you will have, okay, sorry, okay, this is I L, okay, I m, okay, sorry, this is, okay, let me rub this, this has become the same, A, okay, A L B L, okay, and then C I. So, what is A m C m? This is, now I will write this. So, I have simplified now, but this is in initial notation. So, I have to now write in direct notation. So, I will write A m C m is A dot C into vector B minus A dot B into vector C. Okay. So, that is what this A expression A cross B cross C simplifies to. Okay. So, following, so you can see how very nicely I can use the concept of initial notation and permutation symbol to verify certain vector identities. So, next you can try to prove some of the following identities here, okay, which I have given. So, there are 5 identities that you have to prove. Okay. So, you can try it yourself, and if you have any doubt you can always contact me. Okay. Just remember delta here, okay, is E I del by del x I, okay, and because I is repeated, so there is a summation which is involved, okay, and del square, okay, the fourth one, del square is nothing but del dot del, okay, which is nothing but del square by del x I del x I. Okay. So, using this concepts you should be able to prove this 5 identities. Okay. So, next we move to our main topic, which is what is meant by a second order tensor. Okay. So, before defining a second order tensor, you need to notice that there are 2 approaches to define tensors. One is called the functional approach, okay, and the other one is called the operational approach. Okay. So, in functional approach, the tensors are defined without referring to any coordinate system. Okay. So, thus it requires basic understanding of the concepts of linear algebra, like you need to know mapping, okay. And the advantage of this approach is that the tensors can be defined in a standalone manner. Okay. So, tensors can be defined in a standalone manner. Okay. You do not need to take any other tensors or vectors help to define the tensors. Okay. But this approach is not discussed in this course. Okay. This is not discussed in this course because it is a little more involved, and because of time constraint we like to go for the second approach, which is called the operational approach. So, in operational approach, as the name suggests, we go for defining tensors for how they operate on other tensors. Okay. So, in this approach, we require some other tensors to define tensors, okay, other tensors. Okay. So, this is the approach that we follow in this course. So, using this operational approach, a second order tensor A, okay, and when we say a second order tensor, sometimes we interchangeably use the word tensor. Okay. So, when we say tensor, many times people mean only second order tensor. Okay. So, a second order tensor A or simply tensor is defined as a linear mapping that associates a given vector u with a second vector v. Okay. So, what happens? A second order tensor, okay, it operates on this vector u and it gives you another vector v. Okay. So, it is operating on another vector. Okay. Vector is also a tensor, okay, a first order tensor, because it has one index. So, this is called the operational approach of defining a second order tensor. It operates on a vector to give you another vector. Okay. Now, let us see what is meant by the linear mapping. Okay. So, we saw in our introductory lectures what is meant by linear functions. Okay. So, similarly, a linear mapping is a mapping, okay, such that given two vectors u1 and u2 and arbitrary scalars a and b, okay, the resulting vector obtained by taking the linear combination of u1 and u2 given by a u1 plus b u2, okay, and when this vector, let us say c, when this vector c is mapped through this tensor A, you get another vector d, and this vector d will be same as A times A u1, okay, which is the first, plus B times A u2. Okay. So, when that second order tensor A maps the vector u1 and let us say that vector is d1, and when A u2, A tensor A maps u2, let us say we get vector d2. So, d will be equal to A times d1 plus B times d2. So, if this property holds, then the mapping is called a linear mapping, and some of the examples of second order tensor are the identity tensor. For example, I is denoted by symbol I, and this is a tensor, second order tensor, which maps the vector back to itself. Okay. So, it can always happen, you take a vector u and the tensor maps it to itself. That tensor, second order tensor, is called the identity tensor. Another tensor we have already looked into is called the transformation tensor, which rotates vectors in space such that the standard Cartesian base vectors e1, e2, e3 become ei dash equal to q ei, where I goes from 1, 2, 3. Okay. So, the q is called the transformation tensors, okay, transformation tensor. Now, there are some operations on tensors. The first one is the sum of two tensors. So, because we are following the operational approach, we will define these operations through how they operate on vectors. Okay. So, given an arbitrary vector u, the sum of two tensors a and b is defined as a plus b into u is same as a u plus b u. Okay. You remember, sum of two tensors is also a tensor. Okay. Product of two tensors. So, given an arbitrary vector u, the product of two tensors a and b is defined as a into b u is same as a into b u. Okay. So, this can be written in indicial notation, which is given over here. Okay. So, a into b can be written as a I k BKL and then you have UL. So, you can take these two terms in the bracket and you can write AIK BKL UL, which is nothing but BU. Okay. So, I will show what is the direct notation and what is the indicial notation for operations. Okay. So, remember product of two tensors is also a tensor. What is inverse of a tensor? The inverse of a tensor is usually written as A inverse. So, you have given a tensor A. So, its inverse is written as A inverse and this is a tensor which satisfies following property. Okay. So, A inverse gives you a second order identity tensor I. Okay. That is the indicial direct notation, and the indicial notation is AIK, AKJ is delta Ij, where delta Ij is your Kronecker delta. Okay. So, inverse of a second order tensor is also a tensor. Now, another important concept is transpose of a tensor. Okay. So, given arbitrary vectors u and v, the transpose of a tensor is defined as u dot a v. Okay. Just look closely, you have u dot a v, that is how it is defined. Okay. That is how we say the transpose of a second order tensor A is defined. So, u dot a v is v dot a transpose u. So, if a tensor for any arbitrary vectors u and v satisfy this property, then this is called the transpose of the tensor A. Okay. So, transpose of a tensor is also a tensor. Now, we look into one proof. Okay. We will try to prove that the transpose of identity tensor is the identity tensor itself. Okay. So, let us start from the right hand side of the previous expression. Take two arbitrary vectors u and v and we write let I transpose, let I transpose be the transpose of the identity tensor. Okay. So, I can write v dot I transpose u, and now using the definition of transpose of a tensor, I can write this expression as u dot I v. Okay. So, this is using the definition of the identity transpose of a second order tensor. Now, using the definition of identity tensor, I can simplify I v. Okay. So, identity tensor is a tensor which maps a vector to itself. So, I v will be same as v. So, now you have u dot v. Now, I can interchange. Okay. So, I can use the property of dot product of two vectors. So, a dot b is same as b dot a. So, I can write u dot v as v dot u, and now I can write u as I u. Okay. I can write because I u will be equal to u. So, I can use this expression and write v dot u as v dot I u. Okay. So, we started with v dot I transpose u and we have ended at v dot I u. So, if we compare both the expression on the left hand side and one on the right hand side, we can see that I transpose is same as I. Okay. So, this proves that the transpose of the identity tensor is the identity tensor itself. Okay. Now, the task for you is again you start with the following expression u dot I v and try to prove that I is equal to I transpose. I have proven I transpose is equal to I, you prove that I is equal to I transpose. Okay. And another thing is we have done this using direct notation. Try to repeat the same proof using indicial notation. Again, if you have any question, query or doubt, you can always get in touch with me. Okay. So, some other important class of tensors are called symmetric tensor. So, what is a symmetric tensor? A symmetric tensor A is one where A is equal to A transpose. Okay. So, indicial notation we can write A I j is A j I. Okay. A symmetric tensor usually is denoted by symbol S. Okay. What is meant by a skew symmetric or anti-symmetric tensor? So, if A is a anti-symmetric tensor, then A is equal to minus of A transpose, or in indicial notation we can write Aij equal to minus Aj I. Okay. So, usually an anti-symmetric tensor is denoted by symbol W. Okay. And any arbitrary second order tensor is called an orthogonal tensor if the following property holds. Okay. So, if A is a tensor which is a orthogonal tensor, then A transpose will be equal to identity tensor, or A transpose A will be equal to identity tensor, okay, which means that A transpose is same as A inverse, because A inverse is identity. So, this is the indicial notation, okay, for the direct notation that we have written. Okay. So, orthogonal tensor is usually denoted by symbol Q, and that is how you will find in many books that symbol Q is used for orthogonal tensor. Okay. Now, a second order tensor can be, any arbitrary second order tensor can be decomposed into other form of tensors. Okay. So, one such decomposition is called the additive decomposition, where if you are given an arbitrary tensor A, it can be decomposed into what is called a symmetric tensor S and an anti-symmetric tensor W. Okay. In indicial notation, Aij is Sij plus Wij, where S is given by A plus A transpose by 2 and W is given by A minus A transpose by 2. Okay. So, you can check for yourself that S and W are indeed symmetric and anti-symmetric tensor. If S is symmetric, for example, then S transpose should be equal to S. So, you can take the transpose of the symmetric part and try to verify yourself. Okay. Another decomposition which is common, okay, and we will come to it later in kinematics, is the multiplicative or the polar decomposition. So, you are given an arbitrary tensor A. So, you can decompose that tensor into what is called an orthogonal tensor Q and a symmetric tensor S. So, A can be written multiplicatively as Q into S. Okay. So, Q is a orthogonal tensor. So, Q transpose is equal to minus Q, Q minus 1, okay, inverse of Q, and symmetric part S is equal to S transpose. Okay. So, this proof is not very difficult, okay, but it is little involved, and it can be found in standard text on continuum mechanics, which is skipped in this course. Okay. So, with this we will end and we will move to next topic. Okay. Thank you.